All right, so we have all of our formulas, and there's one more that I'd like to give you, and this is for free-falling objects. For free-falling objects, the position function is S of t equals 1/2 times the force of acceleration due to gravity, g, times t squared, plus the initial velocity times t, plus the initial position. This is in your book on page 114. So we've got all of our formulas. Basically, those are the three important ones. They're all in your book. Velocity is the derivative of position. The average velocity is equal to the change in distance over the change in time. And for free-falling objects, the position function, if you're not given one, can be written using this formula, where g is acceleration due to gravity. That's a constant. How many of you have taken or are taking physics? Okay. What's the acceleration due to gravity, force of acceleration due to gravity? 9.81. We use 9.8 here in calculus. 9.8, what's the label? Meters per second, meters per second squared, we usually call it. And did you know what it is in feet? It's 32 feet per second squared. So those are the two different labels if we're using metric or if we're using customary. Customary units are United States. Metric is the rest of the world. So those are the two numbers that we'll use for g, depending on our situation, how it's measured. V sub 0 is the initial velocity. How fast is the object going? This would be something like if I throw a ball. If you throw a ball up in the air, throw anything up in the air, what's going to happen to it eventually? It's going to fall down, okay? So it's not just, a free falling can also be I just drop it. I'm standing at a certain height, or I'm just standing up and I drop something. So that's a free falling, but you can also throw it. So you can have an initial velocity, how fast it's going, and S sub 0 is its initial position. How high off the ground is the object to start with? So now with these formulas, you're going to have to keep referring back to them today. We're going to look at a few examples of problems and solve them. So all right, so let's take a look at these problems here. We're going to start with number 7. Actually, we're not going to do 7. We're just going to start with, we're not going to do any of those. We're going to start with number 11 right here. Okay, so here's our first example. A ball is dropped from the top of a 640-foot building. The position function of the ball is S of t equals negative 16t squared plus 640, where t is measured in seconds and S of t is in feet. And then it says find, part A, the position of the ball after 4 seconds. Okay, so the question asks us about position. Do we have a function for position? Yes. So to answer part A, we know the position function is s of t equals negative 16t squared plus 640. So I want to know the position of the ball after 4 seconds. So any idea of what I might do? Plug 4 in for t. 4 seconds is a time. The t variable in the position function is t for time. So I'm basically finding s of 4. So negative 16 times 4 squared plus 640. Calculators are out and you are typing these in. What do you get? 384. What is the label? S is a what? Position. So it's measured in feet. Exactly. How do you know? It says right up in the problem. S of t, the position is measured in feet. So this is feet. So the answer part A is 384 feet. Okay, part B says find the instantaneous velocity of the ball at t equals 4. All right, instantaneous velocity. What did I tell you instantaneous velocity is? It's in your formulas. It is the derivative. It is the instantaneous velocity, v of t, is equal to the derivative of position. The change in distance over change in time is the average velocity. That's very different than instantaneous. Okay, so what's the derivative of the position function? What's the derivative of negative 16t squared? Negative 32t, and the derivative of 640? 0. So the instantaneous velocity function is negative 32t. But it says what is the instantaneous velocity at t equals 4. So what do I do now? Plug 4 in for t. So s prime of 4 is negative 32 times 4. So the velocity right at 4 is negative 128. What would the label be? Feet per second. A velocity is a speed with direction. That's why there's a negative. It's moving to the left. All right, so now part C says find the average velocity for the first 4 seconds. So what is the average velocity equal to? Change in distance over change in time. Now, to find change in distance, I have to think. I have to say, okay, over the first 4 seconds, okay, at the end, I have to take the position at the end minus the position at the beginning. That's how you find the change in distance. Isn't distance a position? So change in distance, change in position. So I have to take the position at the end time. What's the ending time in this problem? How many seconds have passed at the end? 4. Okay, so you're finding s of 4 minus what is the beginning time after 0. And then you're dividing it by the change in time. How much time went by? 4 seconds. Change in distance is basically you're plugging the ending time and the beginning time into the position function and subtracting. Change in is always a subtraction problem. All right, so s of 4 means go up to this function, s, the position function, and put 4 in. So this will be negative 16 times 4 squared plus 640. minus what I get when I put 0 in. What do I get when I put 0 in here? 640. All over 4. Okay, so are you working this out? What happens to the 640s? They cancel. And negative 16 times 16 is negative 256. Is that right?
Yeah.
Negative 256 divided by 4 is what? Negative 64. What's the label for velocity? Feet per second. So the average velocity over the first 4 seconds is negative 64 feet per second. D. When will the ball hit the ground? When will the ball hit the ground? Have you answered these questions in physics? Let's think about the path of this position function. What is the path of this ball going to look like? Isn't it just kind of going down to the ground? Like that? Isn't that what it's doing? You're dropping it and it's falling? Okay. So at the bottom, what is its velocity down here? Velocity is 0. So when it hits the ground, it's not going any speed. Does that make sense to you? Okay. How far has it gone? It's gone how many feet? 640. How do you know that it's gone 640 feet? Because the building is 640 feet tall. It says that in the problem. Okay. This isn't getting me anywhere really. I need to find when. Are we looking for a time, a position, or a speed? Time. So we're looking for the time to hit the ground. So we're looking for a number of seconds. So how many seconds until it hits the ground? So doesn't both our velocity and position function have seconds, have time in it? So what do I know about the position when it hits the ground? What's its position when it hits the ground? 0. So couldn't I set the position function equal to 0? And then isn't that, if I solve that when I solve for the time, to go from 640 to 0? Yeah. The position when it hits the ground is 0. So I take the position function and set it equal to 0. So now to solve that, I'm going to subtract 640 and divide by negative 16, which gives me t squared equals 40. And then I take the square root of both sides, and that gives me approximately 6.32 seconds to hit the ground. And finally, the last part, the speed of the ball when it hits the ground. So speed is what of our functions? Speed is the same as what? Velocity. So our velocity function is negative 32t. So our velocity function is negative 32t. So what do I need to put into the velocity function to find how fast it's going? 6.32. How long does it take to hit the ground? 6.32 seconds. Put it in there, so v of 6.32. So negative 32 times 6.32 is negative 202.24. What's the label? feet per second.